Hey, so this is our Hexapod robot. I'm Chris, this is Braden, and this is Kevin. So our motivation was to make a six-legged walking and rolling robot, and we wanted to explore with different optimizers and generators for our walking gait and explore different parameters for that. So we looked at simplifying the geometry for more accurate collision detection, and we looked at the endpoint of our foot to track how we're going to walk. And we changed the gait parameters to see how that would improve the walking. So it's a pretty powerful robot that can output 2 kilowatts of continuous power and 12 kilowatts of peak power. We use these types of Xiaomi actuators. They're store-bought, but they came pretty nice. The hardware design is such that all the actuators are near the hip, so it has a low moment of inertia, and it uses carbon fiber tubes and a parallel linkage for the rotation of the foot.
Awesome. Now starting to talk about the SolidWorks URDF pipeline. So Chris here designed a beautiful SolidWorks file, but in order to actually simulate this in Drake, we need to convert it to a URDF file. So I started by using the SolidWorks URDF converter to convert to URDF file. And you can see here, all of these different axes are the defined axes of rotation for each joints. Cool. So now talking a bit about, on the left, we have the original STL file for the leg or for the foot. In the middle is a reduced triangle count mesh. This is so the simulation runs faster for visualization. And then on the right is a convex hole of that same shape. This is actually used for simulation, for collisions in the simulation. So what we come out with is a URDF file. And you can see at the bottom, there's actually spheres at the foot endpoints to be able to track the position of the foot endpoint. So now to talk a little bit about our initial method of path planning. You can see we have sinusoid arcs with straight lines at the bottom, and when we apply this path, the robot walks. We actually use a quadratic cost on our optimization. We use optimization-based inverse kinematics with the quadratic cost, and then we add position constraints on the foot ends, and then that gets us to have our motors moving. So now to talk a bit about path parameters, we have our stride length, which is how far it's stepping with each step, the radius, the stride center point, and then the desired height of the robot base. Here we can see two different heights for the robot base. On the left is a height of 50 millimeters. That gives a stride length of 180 millimeters. On the right is like the highest body height that we were able to have valid inverse schematics for. And it has a stride length of 80 millimeters. Both of these actually have the same walking period. So we thought there has to be some optimum somewhere in between, most likely. So this is where optimization came in, and we actually found that the optimum was a base height of 100 millimeters. This gave a 280 millimeter stride length, which is significantly better than the values we were using before optimization. Same walking period from previous slide. So here's our final results. We can see that it's the longest possible stride versus the height of the robot for various radii. We can see our optimum points on the orange at the 100 millimeters.
Yeah, and so as a different approach, we try to employ a stop solver, which solves a sequence of nonlinear QP subproblems, while still keeping the same prescribed contact schedule, so using a tripod gate with the speed and stride length shown. The stop solver uses gradient information and sparse matrix techniques to be able to solve the subproblems. In this case, we added a bunch of other decision variables to the problem, including center of mass state, angular momentum, foot contact forces, joint positions and velocities, and time steps. We also still employed a quadratic cost on the joint angles, but at the same time, we also had a quadratic cost on the joint velocities. And so with the SNOP solver, we found that the cost function that gave the best results was weighting the leg pitch at 2.5. And we also still had to add symmetry constraints for the hip yaw ankle, as well as anti-symmetry constraints on the hip pitch. And so for rolling, which is another one of our goals, we analytically solved for optimal joint angles, and that gave the robot circular cross section, and we just applied initial velocity. To make this more realizable, we would have to make it self-propel like a virtual rotating oval. And here's just a non-optimal way of rolling, but it was still pretty cool to see. So for future work, we want to develop more reliable body control, as well as add the capability for spinning and turning. We would also like to streamline the deployment of the hardware, as we had major issues, but we're still able to have a good demonstration of the hardware.
This is it jumping. Hey.